Cheers to fellow compilers enthusiasts. Today we will continue developing the bytecode compiler for Fang, and the next milestone is adding support for let bindings, which means adding the necessary instructions to your bytecode instruction set and also adding the environment to the virtual machine. So without further ado, let's switch to the code. Now that we're done with the arithmetics, a good next target would be handling of variables and bindings. If we refer to tree interpreter, we can see that we use the environment to handle variables and let bindings. And this environment is a mapping from variable names to values. Now, when it comes to real machines, there is no concept of an environment, right? So we build environments from much more basic building blocks. But since we're targeting a virtual machine, we can introduce some very high-level instructions for working with the environment, like loading a value from the environment or storing the value in the environment, and let the virtual machine implementer to handle this in the most efficient way or the most straightforward way if you need to be done with things quickly. And this is exactly what we are going to do here. We are going to introduce instructions for working with the environment. So we need a way to load the value from the environment. And the question is, what would be the argument to this instruction? In the AST, we use variable names, which are strings, to kind of map from name to some value. But strings are not the best thing to put into the bytecode. So ideally, we need something with a fixed size. So something like an integer. Basically, we need a way to take all our strings and build an index of the strings and then refer to the string by its number rather than by its name. So let's do this. So the name will actually be a number of the constant. For now, let's make it like a tape alias to just an integer and introduce a ConstPool. So this ConstPool will have two methods. First one, to add the name to the pool and get back its number. If the name is already present, it will not be added again, just the existing number will be returned. That's the idea. And the next method that we will probably need is a way to find name based on its number. Again, string lowercase. Okay, so basically to make this work, we need kind of one or two mappings from names to numbers and back. So I'm going to add the necessary bits and then fill in the method bodies. All right, so now let's actually add a couple more instructions here. So we have end load, then let's have env save. That would take the value from the stack and put it into the environment. Now let's go back to the generate method and handle variables first. So first we need a name number. So actually first we need to add the ConstPool to our bytecode builder. And then we just emit the instruction. Perfect. Now we need to handle the bindings. And we have two cases to cover here. Let's start with not recursive bindings, because these are easier to think about. So what we need to do, we need to generate code for the body. Then we need to save the value of the body into the environment, map it to variable. Then we need to generate the code for the expression. So basically evaluate the expression with the mapping for the LED binding in the environment. And when we are done, we need to actually emit another instruction to restore the previous value of the variable if there was any. Let's maybe drop these. Now to the recursive case. So that one is a bit more complicated. First, before we evaluate body, we need to add mapping from variable to something. And in the case of tree interpreter, we had this black hole value. So if you go down here, we added this mapping from variable to black hole before we evaluate the body, so that if the body actually refers to variable, we have this kind of weird error that the body of the binding refers to the binding itself before it was evaluated, blah blah blah. So anyhow, this is an error that the virtual machine can raise. So if we go back, we can emit the instruction that would put a black hole into the stack. Let's add this instruction. So we go back here. So we meet the black hole. Then we save this as a var into the environment. Then we evaluate the body. Now, since the body is evaluated, we need to update the mapping from variable to the value of the body. So let's say we have one more instruction here. That would be like an update. Okay. So now we generate code for the expression. And at this point, we're again done with the scope of the LED binding. So we just restore what was previously there. So I think in terms of the instructions and the bytecode, we are good. So now we should go to the VM and add the missing pieces. So let's start with the environment first. So the environment will be just mapping from const nums to values. Let's add a couple helpers first. All right. Now we are going to add handlers for the environment-related instructions. Let's start with end load. So here we need to get the value from the environment. And of course, I forgot to add the environment here. And then we need to just push this value onto the stack. And we're done. So the next one is env save. So the process of updating is, so first of all, we need to make the environment mutable here. Surely there are more efficient ways, but this is, I guess, the simplest one. And since we are going to be needing to restore the environment, let's also add an env stack here. Again, this is not something that you will probably see in the production implementation, but for our use case, this will work just fine. Then we take the env stack and we push the current environment to the env stack. Then we update it with okay, and this is it. Next we have env update. And the interesting thing with env update is that it only makes sense if kind of the value of the body is a closure, and we don't actually have closures here. So for our use case, it would be enough to just take the environment and update it directly. And then later on, when we actually add closures, we would need to add some extra handling to this instruction. So finally, we have and restore. Since we have the env stack, it is actually enough for us to do this. And I think this is an interesting case because we see that the bytecode has some information that is not used by the VM. But this information could have been used by the VM or by a different VM implementation that would use the number of the name of the variable that needs to be restored. For, I don't know, if you have a different implementation of the environment, this could be useful. In our case, it is not, and I guess this is just, a very nice demonstration of the value of kind of separating these concerns. The bytecode is separate from the VM. So I think at this point, we should have everything we need. We should have everything we need to unlock the next example here. So here we have LED bindings with arithmetic inside. And if I run the application, the bytecode interpreter should be able to evaluate this. So let's see how it goes. All right, and indeed, it does handle the LEDs plus arithmetic. Actually, it's yeah, it's same value, a little bit faster, so very nice. And just out of curiosity, let's again stop at this breakpoint and see what sort of bytecode we have generated, and what the virtual machine does. So if we run debug, first that's the first example, and now that's the second example. So basically we have 2 plus 3 multiplied by 4 mapped to x, and then 42 mapped to y, and then we have the subtraction here. And so we have 2, 3, 4, multiplication, addition. That's exactly what is happening here. And then we have env save 0. And 0 is the kind of the ID of x in our ConstPool. But the thing is, our bytecode actually doesn't have a ConstPool. So the ConstPool is only present in the bytecode builder. And that's another interesting aspect, that we don't need this information to execute the bytecode, but we would really like to have it for debug purposes. So I think it would be nice to later on extend the bytecode type to have this extra debug information. But that's something we can do later on. For now, I think this looks very, very good. And the only thing that is left is, well, two things. So first, it's abstraction and application, so the handling of functions. And finally, we have conditionals. So very close to the full functioning bytecode compiler and the related virtual machine. To sum up, we have added support for let bindings, doing kind of this co-design between the instruction set and the virtual machine. And although operationally we still have this very sophisticated calculator, there is really just a couple steps between us and the fully functional bytecode compiler and interpreter for Fang. So hopefully next time I'll be able to finish it up and have the full working thing. But right now, I hope this was helpful. Thanks for watching and see you next time. Peace.